almost as if somebody constructed a set of challenging obstacles before us, challenging problems to solve. They're challenging, but they're doable. And there's a sequence to them. Gravity is very difficult to overcome, but we have, given the size of Earth, it's not so bad that we can still actually construct propulsion systems that can escape it.
Yeah. And the same with climate change, perhaps. I mean, climate change is the next major problem facing our civilization, but we know it is technically surmountable.
Yeah.
You know, it does seem sometimes like there has been a series of challenges laid out to progress us towards a mature civilization that can one day perhaps expand to the stars.
I'm a little more concerned about nuclear weapons, AI, and natural or artificial pandemics. But yes, climate change.
Well, there you go. I mean, plenty of
fun
milestones that we need to cross, and we can argue about the severity of each of them. But there is no doubt that we live in a world that has serious challenges that are pushing our intellects and our will to the limit of whether we're really ready to progress to the next stage of our development.
So thank you for taking the tangent, and there'll be a million more. But can we step back to Kepler-1625b? What is it? And you've talked about this kind of journey, this effort to discover exomoons, so moons out there, or small, cool objects out there. Where does that effort stand, and what is Kepler-1625b?
Yeah, I've been searching for exomoons for most of my professional career, and I think a lot of my colleagues think I'm kind of crazy to still be doing it. You know, after 5 years of not finding anything, I think most people would probably try doing something else. I even had people say that to me. They said, professors, and I remember at a cocktail party, took me to the side, an MIT professor, and he said, you should just look for hot Jupiters. They're everywhere. It's really, you can write papers. They're so easy to find. And I was like, yeah, but hot Jupiters they're not interesting to me. I want to do something that I feel intellectually pushes me to the edge, and is maybe a contribution that no one else could do, but maybe is not certainly the thing that anybody could do. I don't want to just be the first to something for the sake of being first. I want to do something that feels like a meaningful intellectual contribution to our society. And so, this exomoon problem has been haunting me for years to try and solve this. Now, as I said, we looked for years and years using Kepler, and the closest we ever got was just a hint for this one star. Kepler-1625 has a Jupiter-like planet in orbit of it. And that Jupiter-like planet is on a 287-day period. So it's almost the same distance as the Earth around the Sun, but for a Jupiter. So that was already unusual. I don't think people realize that Jupiter-like planets are quite rare in the universe. Certainly mini Neptunes and Neptunes are extremely common, but Jupiters, only about 10% of Sun-like stars have Jupiters around them as far as we can tell.
When you say Jupiter, which aspect of Jupiter?
In terms of its mass and its major axis. So anything beyond about half an AU, so half the distance of the Earth and the Sun, and something of order of a tenth of a Jupiter mass, so that's the mass of Saturn, up to, say, 10 Jupiter masses, which is basically where you start to get to brown dwarfs. Those types of objects appear to be somewhat unusual. Most solar systems do not have Jupiters, which is really interesting because Jupiter, again, like the moon, seems to have been a pivotal character in the story of the development of our solar system, perhaps especially having a large influence of the development of the late heavy bombardment and the rate of asteroid impacts that we receive and things like this. Anyway, to come back to 1625, this Jupiter-like planet had a hint of something in the data. But what I mean by that is when we looked at the transit, we got the familiar decrease in light that we always see when a planet travels in front of the star. But we saw something extra. Just on the edges, we saw some extra dips around the outside. It was right at the hairy edge of detectability. We didn't believe it because I think one of the challenges of looking for something for 10 years is that you become your own greatest skeptic. And no matter what you're shown, you're always thinking, it's like falling in love so many times and it not working out.
Right.
You convince yourself it's never going to happen. Not for me. This isn't going to happen. And so I saw that and I didn't really believe it because I didn't dare let myself believe it. But being a good scientist, we knew we had an obligation to publish it. to talk about the result and to follow it up and to try and resolve what was going on. So we asked for Hubble Space Telescope time, which was awarded in that case. So we were one of those lucky 20 that got telescope time. And we stared at it for about 40 hours continuously. And to provide some context, the dip that we saw in the Kepler data corresponded to a Neptune-sized moon around a Jupiter-sized planet, which was another reason why I was skeptical. I was like, that we don't have that in the solar system. That seems so strange. And then when we got the Hubble data, it seemed to confirm exactly that. There was two really striking pieces of evidence in the data that suggested this moon was there. Another was a fairly clear second dip in light, pretty clearly resolved by Hubble. It was about a 5 sigma detection. And on top of that, we could see the planet didn't transit when it should have done. It actually transited earlier than we expected it to, by about 20 minutes or so. And so that's a hallmark of a gravitational interaction between the planet and the moon. We actually expected that. You can also expect that if the moon transits after the planet, then the planet should come in earlier than expected, because the barycenter, the center of mass, lives between the two of them, kind of like on a balancing arm between them. And so we saw that as well. So the phase signature matched up. The mass of the moon was measured to be Neptune mass, and the size of the moon was measured to be Neptune radius. And so everything just really lined up. And we spent months and months trying to kill it. This is my strategy for anything interesting. We just try to throw the kitchen sink at it and say, we must be tricked by something. And so we tried looking at the centroid motion of the telescope, at the different wavelength channels that have been observed, the pixel level information. And no matter what we did, we just couldn't get rid of it. And so we submitted it to Science. And I think at the time, Science, which is one of the top journals, said to us, would you mind calling your paper Discovery of an Exomoon? And I had to push back, and we said, no, we're not calling it that. Even despite everything we've done, we're not calling it a discovery. We're calling it evidence for an exomoon. Because for me, I would want to see this repeat 2 times, 3 times, 4 times before I really would bet my house that this is the real deal. And I do worry, as I said, that perhaps that's my own self-skepticism going too far. But I think it was the right decision. And since that paper came out, there has been continuous interest in this object. Another team independently analyzed that star and recovered actually pretty much exactly the same results as us, the same dip, the same wobble of the planet. And a third team looked at it, and they actually got something different. They saw the dip was diminished compared to what we saw. They saw a little hint of a dip, but not as pronounced as what we saw. And they saw the wobble as well. So there's been a little bit of tension about analyzing the reduction of the Hubble data. And so the only way in my mind to resolve this is just to look again. We actually did propose to Hubble straight after that. And we said, look, if our model is right, if the moon is there, it came in late last time. It transited after the planet. Because of the orbit, we can calculate that it should transit before the planet next time. If it's not there, if it doesn't transit before, and even if we see a dip afterwards, we know that's not our moon. It's obviously some instrumental effect with the data. We had a causal prediction as to where the moon should be. And so I was really excited about that, but we didn't get the telescope time. And unfortunately, if you go further into the future, we no longer have the predictive capability, because it's like predicting the weather. You might be able to predict the weather next week to some level of accuracy, but predicting the weather next year becomes incredibly hard. The uncertainties just grow and compound as you go forward into the future more and more.
How were you able to know where the moon would be positioned? So you're able to tell the orbiting like geometry and frequency?
Yeah, so from the basically from the wobbles of the planet itself, that tells us the orbital motion of the moon. It's the reflex motion of the moon upon the planet.
Isn't it just an estimate to where, like, I'm concerned about you making a strong prediction here, because like if you don't get the moon where the moon leads on the next time around, if you did get Hubble time, couldn't that mean something else if you didn't see that? Like, because you said it would be an instrumental. I feel the strong urge to disprove your own, which is a really good imperative. It's a good way to do science. But like this is such a noisy signal, right? Or blurry signal, maybe.
Yeah.
Low resolution signal, maybe that's the better
Yeah, I mean,
way to say.
it's a 5 sigma signal, so that's at the slightly uncomfortable edge. I mean, it's often said that for any detection of a first new phenomena, you really want like a 20, 25 sigma detection. Then there's just no doubt that what you're seeing is real. This was at that edge. I mean, I guess it's comparable to the Higgs boson, but the Higgs boson was slightly different because there was so much theoretical impetus as to expect a signal at that precise location. A Neptune-sized moon was not predicted by anyone. There was no papers you can find that expect Neptune-sized moons around Jupiter-sized planets. So I think we were inherently skeptical about its reality for that reason. But this is science in action, and when we fit the wobbles, we fit the dips, and we have this 3D geometric model for the motion of the orbit, and projecting that forward, we found that about 80% of our projections led to the moon to be before. So it's not 100%.
Sure.
There was maybe 20% of the cases it was over here, but to me that was a hard enough projection that we felt confident that we could refute which was what I really wanted. I wanted a refutable. That's the basis of science, a falsifiable hypothesis. How can you make progress in science if you don't have a falsifiable, testable hypothesis? And so that was the beauty of this particular case.
So there's a numerical simulation with the moon that fits the data that we observed, and then you can now make predictions based on that simulation.
Yeah.
That's so cool. Okay.
It's fun. These are like little solar systems that we can simulate on the computer and imagine their motions. But we are pushing things to the very limits of what's possible, and that's double-edged sword. It's both incredibly exciting intellectually, but you're always risking to some degree the pushing too far.
So I'd like to ask you about the recent paper you co-authored, an exomoon survey of 70 cool giant exoplanets, and the new candidate Kepler-1708b.
I'd say there's like 3 or 4 candidates at this point, of which we have published 2 of them. And to me, 2 are quite compelling and deserve follow-up observations. And so to get a confirmed detection, at least in our case, we would need to see it repeat for sure. One of the problems with some of the other methods that have been proposed is that you don't get that repeatability. So for instance, an example of a technique that would lack that would be gravitational microlensing. So it is possible with a new telescope coming up in the future called the Hubble Space Telescope, which is basically a repurposed spy satellite that's the size of the Hubble mirror going up into space. It will stare at millions of stars simultaneously, and it will look to see, instead of whether any of those stars get dimmer for a short amount of time, which will be a transit, it'll look for the opposite. It'll look to see if any of them get brighter. And that brightness increase is caused by another planetary system passing in front and then gravitationally lensing light around it to cause a brightening. And so this is a method of discovering an entire solar system, but only for a glimpse. You just get a short glimpse of it passing like a ship sailing through the night, just that one photo of it. Now, the problem with that is that it's very difficult. The physics of gravitational lensing are not surprisingly quite complicated. And so there's many, many possible solutions. So you might have a solution, which is this could be a red dwarf star with a Jupiter-like planet around it. That's one solution. But another solution is that it's a free-floating planet, a rogue planet like Jupiter, with an Earth-like moon around it. And those 2 solutions are almost indistinguishable. Now, ideally, we would be able to repeat the observation. We'd be able to go back and see, well, if the moon really is there, then we could predict its mass, predict its motion, and expect it to be maybe over here next time or something. With microlensing, it's a one snapshot event. And so for me, it's intriguing as a way of revealing something about the exomoon population. But I always come back to transits because it's the only method we really have that's absolutely repeatable, that will be able to come back and prove to everyone that, look, on the 17th of October, the moon will be over here and the moon will look like this, and we can actually capture that image. And that's what we see with, of course, many exoplanets. So we want to get to that same point of full confidence, full confirmation, the slam dunk detection of these exomoons. But it's been a hell of a journey to try and push the field into that direction. And
is there some resistance to the transit method?
Not to the transit method. I just say to exomoons. So the transit method is by far the most popular method for looking for exoplanets. But Yeah, as I've alluded to, exomoons is kind of a niche topic within the discipline of exoplanets, and that's largely because there are people I think are waiting for those slam dunks. And it was like if you go back to the first exoplanet discovery that was made in 1995 by Michel Mayor and Didier Queloz, I think it's true at the time that they were seen as mavericks, that the idea of looking for planets around stars was considered fringe science. And, I'm sure many colleagues told them, why don't you do something more safe, like study eclipsing stars, two binary star systems? We know those exist. So why are you wasting your time looking for planets? You're going to get this alien moniker or something, and you'll be seen as a fringe maverick scientist. And so I think it was quite difficult for those early planet hunters to get legitimacy and be taken seriously. And so very few people risked their careers to do it, except for those that were either emboldened to try or had maybe the career, maybe like tenure or something, so they didn't have to necessarily worry about the implications of failure. And so once that happened, once they made the first discoveries, overnight, everyone and their dog was getting into exoplanets, and all of a sudden the whole astronomy community shifted, and huge numbers of people that were once upon a time studying eclipsing binaries, changed to becoming exoplanet scientists. And so that was the first wave of exoplanet scientists. We're now in a kind of a second wave, or even a third wave, where people like me, to some degree, kind of grew up with the idea of exoplanets as being normal. I was 11 years old, I guess, when the first exoplanet was discovered. And so to me, it was a fairly normal idea to grow up with. And so we've been trained in exoplanets from the very beginning. And so that brings a different perspective to those who have maybe transitioned from a different career path. And so I suspect with exomoons and probably technosignatures, astrobiology, many of the topics which are seen at the fringes of what's possible, they will all open up into becoming mainstream one day. But there's a lot of people who are just waiting for that assuredness that there is a secure career net ahead of them before they commit.
Yeah, it does seem to me that exomoons open wider, or open for the first time, the door to aliens. So more seriously, academically studying, all right, let's look at like alien worlds. So I think it's still pretty fringe to talk about alien life, even on, like on Mars and the moons and so on. You're kind of like, it would be nice, but imagine the first time to discover a living organism. That's going to change. Then everybody will look like an idiot for not focusing everything on this, because the possibility of the things it's possible it might be super boring. It might be very boring bacteria, but even the existence of life elsewhere, that changes everything. That means life is everywhere.
Yeah. If you knew now that in 5 years, 10 years, the first life would be discovered elsewhere, you knew that in advance, it would surely affect the way you approach your entire career. Especially someone junior in astronomy, you would surely be like, well, this is clearly going to be the direction I have to dedicate my classes and my training and my education towards that direction.
All the new textbooks, all the have to be written. And I think there's a lot of value to hedging, like allocating some of the time to that possibility, because the kind of discoveries we might get in the next few decades, it feels like we're on the verge of a lot of getting a lot of really good data and having better and better tools that can process that data. So there's just going to be a continuous increase of the kind of discoveries that will open. But a slam dunk, that's hard to come by.
I think a lot of us are anticipating. We're already seeing it to some degree with Venus and the phosphine incident. But we've seen it before with Bill Clinton on the White House lawn announcing life from Mars. And there are inevitably going to be spurious claims, or at least claims which are ambiguous to some degree. There will be, for sure, a high-profile journal like Nature or Science that will one day publish a paper saying biosignature discovered or something like that on TRAPPIST-1 or some other planet. And then there will be years of back and forth in the literature. And that might seem frustrating, but that's how science works. That's the mechanism of science at play, of people scrutinizing the results to intense skepticism. And it's like a crucible. You burn away all irrelevances until whatever is left is the truth. And so you're left with this product, which is that, okay, we either believe or don't believe that biosignatures are there. So there's inevitably going to be a lot of controversy and debate and argument about it. We just have to anticipate that. And so I think you have to basically have a thick skin to some degree academically to dive into that world. And you're seeing that with phosphine. It's been it's been uncomfortable to watch from the outside, the kind of dialogue that some of the scientists have been having with each other about that, because
they get a little aggressive.
Yeah, and you can understand why, because
jealousy? I don't know. That's me saying, not you. That's me talking.
I'm sure there's some envy and jealousy involved on the behalf of those who are not part of the original discovery.
Sure.
But there's also, in any case, just leave the particular people involved in Venus alone. In any case of making a claim of that magnitude, especially life, because life is pretty much one of the biggest discoveries of all time that you can imagine scientifically. You can see, and I'm so conscious of this in myself when I get close to, as I said, even the much smaller goal of detecting an exomoon, the ego creep in. And so as a scientist, we have to be so guarded against our own egos. You see the lights in your eyes of a Nobel Prize, or the fame and fortune and being remembered in the history books. And we all grew up in our training learning about Newton and Einstein, these giants of the field, Feynman, Maxwell. And you get the idea of these individual contributions which get immortalized for all time. And that's seductive. It's why many of us with the skill set to go into maybe banking instead decided, actually, there's something about the idea of being immortalized and contributing towards society in a permanent way that is more attractive than the financial reward of applying my skills elsewhere. So to some degree, that ego can be a benefit because it brings in skillful people into our field who might otherwise be tempted by money elsewhere. But on the other hand, the closer you get towards when you start flirting with that Nobel Prize in your eyes, or you think you're on the verge of seeing something, you can lose objectivity. A very famous example of this is Barnard's star. There was a planet claimed there by Peter van der Kamp, I think it was in 1968, 69. And at the time, it would have been the first ever exoplanet ever claimed. And he felt assured that this planet was there. He was actually using the wobbling star method, but using the positions of the stars to see them, to claim this exoplanet. It turned out that this planet was not there. Subsequent analyses by both dynamicists and theorists and those looking at the instrumental data established fairly unanimously that there was no way this planet was really there. But Peter van der Kamp insisted it was there, despite overwhelming evidence that was accruing against him. And even to the day he died, which was, I think, in the early 90s, he was still insisting this planet was there, even when we were starting to make the first genuine exoplanet discoveries. And even at that point, I think Hubble had even looked at that star and had totally ruled out any possibility of what he was talking about. And so that's a problem. How do you get to a point as a scientist where you just can't accept anything that comes otherwise, because it starts out with the dream of fame, and then it ends in a stubborn refusal to ever back down.
Of course,